So this is what we have been discussing. In past few classes, we have seen the details of this particular system and the corresponding phase diagram. Okay. And now that we have understood the different phases and also the phase boundaries that we have, I think now it is time for us to look at some of the phase transformations in this particular system. Okay. And these are the transformations which actually lead to different grades of steels as you heat treat these iron carbon alloys in different conditions. As you could see from this diagram, if you choose any of those temperatures and a particular phase field and heat treat the steel in those conditions, then you can generate a particular type of microstructure that can give rise to a particular grade of steel having certain properties. Okay. So this is how the whole steel technology is based upon this particular diagram, and that is how you can create different types of microstructures, right, by doing some heat treatment in different phase fields at different temperatures. Okay. So we would take up this one first, the one that we have been discussing, the eutectoid transformation. And as I said, this is what primarily forms the basis of the heat treatment and microstructure development in steels. Okay. So we have already seen what a eutectoid transformation is, okay, and what do you get in the microstructure. How does the microstructure develops depending on the composition, whether you are having a hypo-eutectoid composition or a hyper. Based upon that, the microstructure would develop starting from the formation of the first solid phase from another solid phase. It could be either the alpha ferrite phase in case of hypo-eutectoid, and in case of the hyper-eutectoid, the cementite phase will first start forming from the gamma phase. Okay. And we have seen how the microstructure would develop and what would you see in the final microstructure depending on the composition. Okay. Now we will have a look at this particular transformation that you have. Okay. This austenite to pearlite. As we have seen, it develops in this kind of morphology or shape, right. The grains of pearlite would look something like this, as you could see in this schematic, a lamellar kind of structure where you see these lamellae of ferrite and cementite, alternating lamellae of ferrite and cementite in these grains. Okay. So if you have a 100% pearlitic structure, that is the 0.8% carbon steel, then all around the microstructure you would see these lamellae. On the other hand, if you have hypo or hyper-eutectoid compositions, then apart from the pearlite, you would either see the pro-eutectoid alpha phase or the pro-eutectoid cementite phase. Okay. And how does it exactly look like in the microstructure? We have already seen an example of that. So now we are going to see as to what is the mechanism and how it occurs during this transformation. And why does it lead to this kind of lamellar structure? We would also get an idea about it as to why this kind of lamellar structure develops for this kind of transformation. Okay. So having a look at the mechanism, we will throw some more light onto it as to why it happens like that and why it develops in this particular morphology. Okay. All right. So what we are talking about here is this eutectoid transformation. Where the austenite phase is transforming into two new solids, ferrite and cementite. Okay. And this is occurring at 727 degrees Celsius and at a composition of around 0.8% carbon. Okay. So now you could see, although the composition of the solid which is transforming into two new solids is 0.8% carbon, but the composition of the individual solids which are forming is very different, right? One is very low, around 0.02% or 0.025 to be more precise. And another one is much higher compared to that, 6.67% carbon. Okay. So what does that tell you? That basically tells you that this 0.8% carbon that you have, okay, that has to redistribute between these two phases, right? Because one is having much lower carbon compared to the other one. Okay. So the first thing that has to happen for this transformation to occur is redistribution of the carbon content. Okay. And that basically comes down to the diffusion phenomena, right? The carbon has to go through the diffusion process, and then these two phases will form, one with low carbon content and another with high carbon content, right? So for the ferrite phase to form, you can see that the carbon content has to reduce, and for the cementite to form, the carbon has to increase, right? So what does it tell you? It tells you that the carbon has to diffuse to the cementite phase. Okay, so that would be the direction of the movement of the carbon atoms, right, or the direction of diffusion. So this phase will start forming at the existing austenite boundaries, right? So if you have a boundary like this, here you have the austenite phase on both sides of this boundary. So on this boundary, a small grain of this pearlite will start forming, right? And then it will grow in one of these austenite grains, depending on which side it is high energy and which side it is low energy. So it will grow towards the high energy boundary region to reduce the energy of the system. Okay. Now, when it grows, as I said, the carbon has to redistribute between these two phases. So if it forms like this, a cementite followed by a ferrite lamellae. So if it forms like that, let's say around this region, it is forming in that manner. Through this schematic, let us try and understand that. So this black one that you see over here, that is the cementite phase, this shaded or the black strip, and the white region in between you have the alpha phase, the ferrite. Okay. So as I said, it grows in alternating layers. So what happens when let's say the ferrite phase is first forming, okay, during this transformation. We are here, right? This is 0.8%. And we are also at the eutectoid temperature. So if you go by the free energy change and all that, then at that temperature, all the three phases are stable: austenite, ferrite and cementite. So the conditions are such that these two phases of pearlite, ferrite and cementite can form. I mean, they are stable at that particular temperature. As you go little below that, then only these two phases will be stable, ferrite and cementite, right. So, the austenite has to convert to ferrite and cementite, right. Okay. So, if the ferrite forms, then you can see that from 0.8% carbon, it is reducing to 0.025% carbon. Okay. So, that extra amount of carbon which is given out by the austenite phase to form the ferrite phase, that has to now diffuse, right. So, it will diffuse to the surrounding region where the ferrite is forming, and then as the carbon content keeps on increasing,
the moment it goes over a critical concentration,
the cementite lamellae will nucleate. Okay. And then as the cementite lamellae forms, it is consuming all the carbon around it, right, the extra amount of carbon, and therefore, the carbon content around the cementite lamellae is reducing, isn't it? And the moment it reduces
below a critical concentration,
then again a ferrite lamellae will nucleate, and this process continues. Okay. So, this is why this develops in this lamellar fashion. For the formation of the alpha phase, carbon is rejected because carbon content is much lower than 0.8%, and for the formation of cementite, you have to provide more carbon because it is more than 0.8% carbon. Okay. So, that is why it is alternative. When it is being rejected, when the carbon is being rejected, it is consumed for the formation of the cementite, and when the cementite has formed, you know that all the carbons which were rejected is now consumed, and therefore, the carbon content around the cementite lamella has decreased significantly, and that would lead to the formation of ferrite. Okay. So, basically what we are saying is, in terms of the carbon redistribution, if you see, we are starting with this 0.8% carbon, which has to be redistributed between these two phases which are forming, that is ferrite and cementite. Okay. So, when the cementite is forming, let us say cementite lamellae has formed in the austenite grain, because of high carbon content in the cementite, it is consuming lot of carbon from the austenite grain, and as a result of that, the carbon content adjacent to this cementite lamellae will decrease, okay, from 0.8%. So, if you come down from here close to this, then the carbon content will decrease, right, something like this. So, let us say this is the carbon concentration which is required for ferrite nucleation. Then as it goes down, as the carbon concentration goes down near the cementite lamellae, it will create favorable condition for nucleation of a ferrite lamellae close to it, just adjacent to it. Okay. Similarly, when the ferrite lamellae forms, then since it has a very limited amount of carbon, the carbon concentration around it will start increasing. Okay, and that would lead to the condition for nucleation of another cementite lamellae, and this process will again repeat. So, that is how it grows into alternating layers of ferrite and cementite in that fashion what you see over here in this particular schematic. Okay. So, when the ferrite lamellae grows, then this is how the carbon concentration would vary. So, when the ferrite lamellae grows in this manner, then as I said, near to it the carbon concentration would increase, right, because it will reject the excess amount of carbon that it does not need. It needs only 0.025% carbon. Rest will be all rejected around it. So, there will be a buildup of carbon content adjacent to the ferrite lamella which is growing. So, that carbon would be utilized to grow another cementite lamellae. And depending on whether cementite or ferrite is forming, it could be either consuming carbon or it will reject carbon. Okay. If it consumes carbon, then you know that the carbon content is going to decrease around that lamellae, right. So, that will create condition for the nucleation of the ferrite phase, because it has lower carbon content. Similarly, other way around, if ferrite forms, the carbon content around the growing ferrite lamellae would increase, because it has to reject all the excess carbon that it cannot accommodate. So, that will create a condition just adjacent to it for the growth of a cementite lamellae. If you want to know which phase is forming first at the austenite grain boundary, that depends on the composition. It could be a 0.5% carbon steel, for example. It could be 1.1% carbon steel on the other side, that is the hyper eutectoid. Okay. So, that is one factor which will decide which phase will form first, whether ferrite will form first or cementite will form first. So, there could be these 2 or 3 scenarios. One, ferrite is forming first, that is very obvious for all the hypo-eutectoid steels. Similarly, for the hyper-eutectoid steels, cementite will nucleate first. Okay. Then on the boundary to start with, on the austenite boundary to start with, you could have a pro-eutectoid ferrite, you could have a pro-eutectoid cementite phase already formed. There could be situations where the boundary is clean. The pearlite phase is growing on a clean boundary which did not have either of these phases, either cementite or ferrite. So, this could be the 3 scenarios depending on the composition of the steel. So, what would be the direction of the carbon diffusion if you see parallel to this growing front? So, this is the direction of the growth, right. So, if you look at parallel to this growth front, what will be the direction of the carbon diffusion? So, if a alpha lamella has formed over here, this white region, right, then it is only 0.025%, which has come down from 0.8%, right. So, the carbon is moving, right, it is getting distributed from 0.8% to 0.025%. If that much carbon concentration has come down, what is happening to the carbon? The excess amount of carbon which is being given out by the ferrite phase, it has to diffuse. Where it could diffuse? Where the carbon can be consumed. Okay, so it will diffuse to a phase which can accommodate more carbon. And what is that phase? That phase is cementite. So, that arrow over there, what you see, that is the direction of carbon diffusion from the ferrite lamellae towards the cementite. Okay. And as you could see from here, as I was mentioning, this would also ensure that the diffusion distance for the carbon atoms is also kind of minimized, right. It does not have to really go through a large diffusion path for this transformation to occur. So, that will make sure that the transformation proceeds without much of difficulty, at least in terms of the redistribution of the carbon atoms. Okay. All right. So, that was about the Pearlite transformation.